In this lesson, we're going to examine the next stage of trigonometric equations, ones that involve quadratic type situations. I know they're quadratic type situations when I have two different trig expressions being multiplied together. So for instance, if I were to see sine x times a different one, like cos x, that's going to be a quadratic situation. It's kind of like in the old days, x times x would make x squared. Obviously, these are the same and these are different, but they both result in the same kind of situation and how to solve them. What I need to do is think back to quadratics. In quadratics, if I had, for instance, a nice factored equation look like this, and I said I want to solve it, I would have to find my zeros, make each part equal 0. The same is true for trigonometric expressions. If it comes up to 0, then either that equals 0 or that part equals 0. And if I can separate my question into two different parts, I can find each solution independently. So let's take a look at this first one here. Okay, I want to solve, and my answer is going to be between 0 and 2 pi. I have an expression that's equal to 0. Well, it's equal to 0 only if either this part comes out to 0 or this part comes out to 0. And I know that's true because the only way I can come out to 0 by multiplying is if one of the two things happens to be 0. Now I have two separate questions. I'm going to treat these as two separate questions. The answers, the combined answers, are the answers of the entire problem, but for these two separate questions to work with. So the first thing I do is think about cos x being 0. Well, 0 is a special one, right? This is when my x is that and my y and my r is that. That is one that comes out on a axis. Okay, where is x 0? Well, 0 down here and 0 up here. So the answer to this part of the problem is either pi over 2 or 3 pi over 2. But unfortunately, that's not the only part of the problem. I also have this piece up here. To solve this, I have to go back to thinking about linear expressions and putting numbers on one side and letters on the other. That again is a problem that can be solved using my cast rule, A and S. I got my y value is root 3, my r value is 2. That makes this a special triangle. And the answers to this part of the problem, again, there's two of them. The first one is pi over 3. That would be your first quadrant. And the next one would be 2 pi over 3 in the second quadrant. So this question, part A that we started with, actually has 1, 2, 3, 4 different answers. And that would be true or typical of most quadratic questions. You're going to have multiple answers. Not necessarily 4, but you're usually going to have more than 2, like we do with linear expressions. Let's try part B. In part B, I have two things being multiplied together and it comes out to 0. That's only true if either sine x is 0 or cos x is 0. One of those or both of them have to be 0 to get an answer of 0. Two separate problems. Okay, where is this one 0? I need my y to be 0 this time. Well, that happens here and here, right? Negative 1, 0, and 1, 0. So our solutions are either 0, pi, or 2 pi, if I go all the way around, right here, to 2 pi. If I try the other hand, we've already done this one. It's the same answers we did over here. So I'm going to cheat and write down the answers. I know what they are. Pi over 2 and 3 pi over 2. This question has 5 different answers. It turns out if you land on an axis at any point, whether it's 0, pi over 2, pi, 3 pi over 2, or back to 2 pi, and you plug it into your equation, you're always going to come out to a 0, because one of the two numbers is 0. Let's take a look at some other ones. What else can we do with this? I'm going to look kind of more like quadratics. The idea that we might have to factor things is going to come into play. If I look at C, I can't add those together because they're not like terms, but they have something in common, which means I can common factor. If I take out a sine x, I'm left with that expression. I can separate it into two separate parts. Either that equals 0 or 3 sine x plus 2 has to equal 0. Two different things to solve. Sine x equals -2. If I bring the 3 over and divide it, I get -2/3. This one we've already solved, but just to point it out again, my y value is 0 on here and here. Right, -1, 0, and 1, 0. So my solutions are 0, pi, and 2 pi. But the right-hand one, when I go to draw my special triangles, C, A, S, and T, it turns out that I have an R value of 3. We know that doesn't come from a special triangle. So I need to combine my ideas of using calculators. And if I want to find the angle, I can say sine A equals 2/3. So A is the inverse of 2/3. Make sure my calculator is in radians, of course. I type that in, I get 0.730. And that's A, not our answer, it's A. Our answers are pi plus A, which comes out to what, 3.871. And the second answer would be x equals 2 pi, would be all the way around, but I stopped short of that by A, 0.730. Put that in my calculator, and I got 5.55. Okay, so I can combine my old ideas of being able to use rotational trigonometry with special triangles, and again with the calculator at times. It depends on the situation. Okay, I get you guys to try D. D is something that needs factoring. What kind of factoring is it going to need? Well, looks to me like a complex trinomial. You need to multiply to -12 and add to 1. Numbers that do that, 4 and -3. So I need to replace around a room here, so I'm going to move some stuff around. 3 cos. And we're using our decomposition method here, so we're going to break down by common factoring. Sorry, not 3, it's a 1. And then I know I'm on the right track because my brackets match. They do match now. And my leftover stuff was my other bracket. Okay, ready to be solved. Haven't solved yet, it's got ready to be solved. My solutions are either 3 cos x plus 1 equals 0, or 4 cos x minus 1 equals 0. If I solve this for cos, I'll get -1/3. I solve this one for cos, I'll get 1/4. And unfortunately, I don't believe either of those are special triangle questions. So I'm going to have to use my cast rule without actually, just move this out of the way, without actually using the special triangles. So where's cos negative? These quadrants. I need that angle A and that angle A. And for the cos being positive, I'll need those quadrants, that angle A and that angle A. Let's do the left-hand one first. So cos A equals 1/3. So A is my inverse of 1/3. And with my calculator in radians, I got 1.23. Those are my answers. My answers are x equals pi minus 1.23 and x equals pi plus 1.23. I got this one and that one. So with my calculator, I got 1.91 for that one and 4.37 for that one. I have to do the exact same math for the other triangles. Okay, for the 1/4 one now. Let's give that a try. Cos A equals 1/4. And we're solving to redraw those two triangles with these two A values. So I'll take the inverse of that, and I got 1.32. Now, nice news is that's one of my answers. So x 1.32. The other one will be 2 pi minus 1.32, and I need to go to there only. And that comes out to, I believe, 4.97. Okay, so we're getting the hang of this. Hopefully we've got some factoring going on now. We still use the same ideas we do with quadratics, and for that matter of polynomials. We're just doing it with trig expressions instead. Let's try someone a little more complicated. And we're just going to play with these today. Nothing, no new math, just playing with this math. Okay, what do I notice when I look at this expression? Well, I notice they both have a 2 in them. They both have a sign in them. So if we can, we like to common factor. Because then either this equals 0 or this equals 0. Now, the first one I can divide by sign, divide by 2 I should say, I get that, which we like. Okay, that's a y being 0, y is 0 here, y is 0 here. The answers, we've done this one a few times now, are 0, pi, and 2 pi. This other one, however, special triangles for a secant, that's your r. An r being a root 3 is not something we usually have. Okay, so I'm going to have to flip this. I'm going to have to think of this as that. But again, I'm not used to having an r as a root 3, which means I need to use my calculator. So I'm taking the inverse cos of 1 over root 3. I get 0.955. Well, I guess I shouldn't call it x, right? This isn't actually angle x. It's actually angle A. Or that's for A. Now it turns out that one of them is the x, right? Because one's the nice quadrant, the first quadrant here. So x is technically 0.955. But the other one, the 2 pi minus, different answer. You should get 5.328 for the 2 pi minus one. Okay, I'm hoping this is going okay so far. Anyway, one more big idea. And so we've set them equal to 0. We've done some nice factoring. The one last thing we have to do sometimes is you might, just might, need to apply some identities. So they could be the simple ones that we know from last year, 2 basic ones. It could be a compound angle or a double angle to actually solve these things. The reason I might have to do that is maybe I can't factor it the way it is. Maybe I can't isolate my trig ratio. If that's the case, you need probably to think about one of these new ideas. Okay, so let's start with something new. Again, I'm still solving. I want to solve for that. I get a question that looks pretty good. Tan 2x equals negative 1 over root 3. Well, that's not something I'm quite familiar with. The new thing is this weird thing here in the middle, the 2x. But if I change the question, and I say to myself, I just want to know what angle makes this work. That's something I can solve. In fact, that's a special triangle. Okay? Tan being negative, text. Tells me that angle A, now notice I'm saying angle A, that's what I solved here, right, is this, which is, what's that, 5 pi over 6. Or A could be, if I go all the way around to here, not quite 2 pi, it's going to be 11 pi over 6. It'd be great, that's what angle A is. My question didn't actually have an A to begin with. It had 2x. I just happen to replace the 2x with an A. So in other words, I could say that, well, if A is 2x, then this must be true. And if that's true, then x, divided by 2, is actually 5 pi over 12. So I can solve for an angle by changing the question sometimes to make it something more familiar. Now notice we've got 2 different answers here. So I need to have both parts. And I can solve them. Okay, so that's one weird thing we can do, where I didn't necessary to use an identity per se. It didn't change the question. I just changed the format of it to make it something simpler to solve right off the bat. Now, if I look at the next one, I could try doing that. I could say to myself, okay, well, let's do negative 2 cos A equals 2 sine x. But the problem with that is I've got two different things. And even if I rearrange them and put them all together on one side, well, now I've got an A with an X, and oh, those are different, and I can't do that this time. So I need to apply a different idea. What else can I do with this? Well, I kind of want to get rid of a double angle like I did over here. And I notice that this is a double angle. So what do I know about cos 2x? Well, I know that cos 2x, one of its many arrangements, is 1 minus 2 sine squared. And since this question already has sines in it, it might make more sense to change my question. I'm going to replace cos 2x with that. So what's that going to look like? 1 minus 2 sine squared x equals 2 sine x. So now my expression only involves sines. It's not ready to be solved yet because I have to get rid of my brackets. It's a quadratic, so I kind of want to make them equal to 0 before I start. Probably want to put this in the right format too. So I got 4 sine squared minus 2 sine x minus 2 equals 0. That looks like a trinomial that can be solved. What can I do to solve this trinomial? Well, I can definitely make it easier. Divide it all by 2. If I do that, I've got a trinomial still, a simpler trinomial, that maybe can be factored. It looks like a complex trinomial. If I multiply those together, I get negative 2. I got to add to negative 1. Are there numbers that do that? Sure there are. Negative 2 and positive 1. So I do my replacement. This 2 is just going to hang out the front. And a common factor. Common factor again. And I notice that I have a common bracket, which is great news for me. So I'm going to write that part out. And now I'm ready to solve. What's going to make this equal 0? Well, either this equals 0 or this equals 0. If I solve this one for sine x, I'll get negative 1 over 2. This one is just sine x is 1. We like these ones. When y and r are both 1s, I mean they're on an axis. Where is y1? That's the only spot. So x is pi over 2. Try the next one. Looks like a cast rule. C is negative. T is negative. Y and r. 1, 2, and a root 3, which makes this pi over 3, which makes this pi over 6. Okay, what are my answers for that triangle? I got 2 of them. I've got a little bit past 180. So pi plus 180. Sorry, pi plus pi over 6, which is 7 pi over 6. Or 2 pi minus pi over 6, which is 11 pi over 6. Ooh, all kinds of good stuff on that one. We had to think about an identity to make it easier to begin with. I think the bottom half of the question is not bad. It's the top half we have to think a little bit about. And that's our objective, is to think. Okay? We don't really want to work in doubles. So either if we can just get rid of them right off the bat, it's nice. If not, get rid of them in a way that will help you. Right? We want our ratios hopefully to be the same, because then we can factor or collect like terms or do other things with it. All right, I got one more for you. I'm going to get you guys to try this one. Solve this. 2 sine squared minus tan squared. I don't see any double or compound things going on there. I can't factor, common factor, because those are different things. So what else can I do with this? Well, I may have to go back to identities again. We know that tan is sine over cos. So tan squared is sine squared over cos squared. Now, why would I want to do that? Well, it means that I have something in common between these two things. To add fractions or subtract fractions together, I need to have a common denominator. But whatever I do to the bottom, I have to do to the top. I'm going to turn this into a single fraction so I can make it easier to solve. So I have 2 sine squared x cos squared x sine squared x over my 1 fraction. It's ready to be solved. What can I do to solve this? Well, cross multiply. We're left with just the top part. In the top part, I notice that they both have a sign in them. In fact, a sine squared. So if I take that out, I've got something that's factorable. So either this has to equal 0 or this has to equal 0. So how am I going to solve those? Well, sine squared means I have to square root it. Square root of 0 is still 0. That one's nice. Where's y 0? Right there and right there, as we've seen more than once. So 0, pi, 2 pi. When I do this one, the cos by itself, I'll get 1 over 2, but it's cos squared. So I'm going to have to square root it. When I square root something, it could be a plus or a minus. And square root of 1 is 1, square root of 2 is root 2. So to think about that, I now have to draw my special triangles in both the positive and the negative spots. So in other words, everywhere. There's my x, there's my r, root 2, root 2, root 2, root 2, 1 and 1. Hey, that's a special triangle. That's a triangle's got pi over 4 in it, in all 4 spots. So what are my answers to that question? Well, x could be pi over 4, or 3 pi over 4, or 5 pi over 4, or 7 pi over 4. And this question actually has 7 different answers. Okay, that's the end of quadratic equations. That's a lot of stuff in there, right? Okay, we have to think about factoring, we have to think about rearranging, we have to think about identities sometimes. Okay, use your calculators at times, special triangles, it's kind of combining everything we've always done. Okay, a couple questions to try. I know these take a while, so there's not a ton there, but I do need you to practice them.